Hello everyone, it's Ishwarya Surana, student of IAPS MTech DABV. Today we'll solve some question of numerical analysis and design. We'll begin with the first question. Here the value of function is given at different points: 0.25, 0.25, 0.26, 0.27 and 0.28, and we need to find the derivative of this function. Okay, so when the value of anything is given at different points, we can write it, the function, as fx is equals to f of x1 plus forward difference of f1 by h into x minus x1 plus second forward difference of f1 upon factorial f into h square into x minus x1 into x minus x2 plus rx, where rx is the relative error. Now we'll differentiate with respect to x, as fx is a constant, it is 0, and then we'll differentiate this x minus x1 term, we'll get 1 here. Similarly, differentiating this with product rule, we'll get x minus x1 plus x minus x2. Here now what is rx? So rx is the relative error, which can be represented as f3a into x minus x1 into x minus x2 into x minus x3 upon 3 factorial. So when we differentiate this, rx will get this the whole big equation by applying the product rule. Now we need to find here the derivative at value x3. So we'll take x is equals to x3 and substitute in place of this x, x3. So x3 minus x1 and x3 minus x2 would be with us. Now as we know that x3 minus x2, that is the difference of successive values, is equal to h, and x3 minus x1 is equals to 2h. So we'll find the value of the derivative at x3, and we will have forward difference of f1 upon h plus second forward difference of f1 upon 2h square into x3 minus x1, that is 2h, and x3 minus x2, that is h, and the relative error. Now the forward difference of f1 is equals to f2 minus f1 upon h. Second forward difference is f3 minus f2 plus f1 upon 2h square into 3h plus the relative error here. Then on solving this further, we'll cancel out this h, we'll left with 3 here and 2h here, the relative error here. Here also we have done 2h and h, 2h and h, so we have 2h square, and finally this f3a h square by 3. Proceeding further, we have now when we solve it further, we'll get 2f2 minus 2f1 plus 3f3 minus 6f2 plus 3f1 upon 2h, and when we plus minus it, difference sum it, will get f1 minus 4f2 plus 3f3 upon 2h and the relative error. Now by equation 1, so what's equation 1? This. By equation 1, that is this one, will get this thing, that is df by dx at x is equals to x3 is equals to forward difference of f1 by h plus 3 times of second forward difference by 2h plus the relative error. Now in this equation we need to find forward difference of f1 and second forward difference of f1. So we'll make this table. The forward difference is obtained by fi plus 1 minus fi, that is successive minus the previous one. So we'll get we'll subtract this 2, that is 0.2571 from 0.2474. We'll get 0.0097. Subtracting it further, we'll get minus 0.0001. Here while going till del square f, that is the second forward difference, we'll get the values nearly equal to 0. So we'll not continue further like finding the third forward difference, and we'll stop it here. Now again here we need to find the value of h. So h is x2 minus x1 or x3 minus x2, we can do anything. So x3 minus x2 is 0.27 minus 0.26, that will be equal to 0.01. We'll substitute this all these values in this. Now here del f1 is equals to 0.0097 upon h, which we have found out 0.01 plus 3 times of second difference of f1, that is 0.0001 upon 2 into 0.01 plus relative error. Okay, so finally we will get 0.9550. Again, in the next time we have to find the second difference, that is second derivative of this same function. So we'll use the first derivative, differentiate it again, and we are left with the second derivative, that is f1 upon del f1 upon h square plus the relative error, double differentiation of the relative error. Again we'll differentiate the error term, that is r double dash x, and we have got f3a into x minus x1 plus x minus x2 plus x minus x3 upon 3. Here we have applied the product rule of the differentiation. So here the double differentiation of this function at x1 is del f1 upon h square, and when we have put the values of f1 and h square here, we will finally get 0.0097 upon 0.01 and plus the relative error term. When we neglect the error term, we will get 0.97. Okay, so here we'll get first derivative and second derivative of this sine function. Now the second question. Here we need to integrate the function here tabulated using Simpson rule. Now as we can see that the function is tabulated at 10 points, and the restriction of Simpson rule is just that it will operate only on odd number of points. So we cannot apply Simpson rule directly on even number of points. Hence, to make it odd, we leave the first point and solve it using trapezoidal rule, and the remaining 9 points using Simpson rule. Also, trapezoidal rule will require 2 points, so we will use this 2 points, that is 4 and 2 of 0.6 and 0.5 interval. Will integrate the function within the limit 0.6 to 0.5 here. Okay, and yeah, here it is. And according to trapezoidal rule, we know that h by fx, that is integration of any function, is equals to h by 2 into y0 plus yn plus twice of all the midterms. Here y0 is equals to 4 and y1 is equals to 2, which is also equals to yn. It is the second and the last term. We have done it here. H is equals to f minus f0 is equals to 0.1. So from equation 1 we'll get 0.1 upon 2 into 6, that is equals to 0.3. Now this value of integration is just for the first point. For the second point, from the second point till the 10th point, that is total of 9 points, we will use the Simpson rule. According to Simpson rule, we will have integration of any function from 0 to n. We have h by 3 into f1 plus 4 times of all the even terms plus 2 times of all the odd term plus the last term. Okay, so here we'll integrate it from minus 0.5 to 0.3 into is equal to h into first term, that is 2, plus 4 times of all the even terms, that is, okay, so what are the even terms here? Here even terms are 3, 4, 2 and 5, and the odd terms will be 3, 2 and 8. So here odd terms 3 minus 2 and 8 are multiplied by 2, and all the even terms, that is 3, 4, 2 and 5 are multiplied with 4, and the last term is added then. So here we'll get on solving it again and again, we will get the value 2.8 of this integral. will add both these integral, that is from 0.5 to 0.3 the value of integral, and from 0.5 to and from 0.6 to 0.5 the next integral, will get 3.1 here. So the value of the function and this interval is 3.1. Now the next question. In this we need to solve the equation using Gauss-Jordan method. Three equations are given. 2x1 plus 4x2 plus 2x3 which is equal to 15, 2x1 plus x2 plus 2x3 is equal to minus 5, 4x1 plus 2x2 minus 2x3 is equal to 0 will form a matrix with these coefficients 2, 4, 2, 2, 1, 2, 4, 1, minus 2, and it's equal to value that is 15, minus 5 and 0. So here we are having a 3 cross 4 matrix with us. Gauss-Jordan's method concept is to diagonalize the matrix and make it an identity matrix, and finally having the values of x1, x2 and x3. First I'll apply row transformation, making row 1 as a pivot element. I'll subtract R1 from R2 and transform R2. So I'm left with 0, minus 3 and 0. Basically I have to make the elements, all the elements 0 except the diagonal elements. Okay, so here I have made both these 0 and minus 3 is only left. Okay, now what I can do is again as I have made row 1 as a pivot row, so I will use the same row using I will use the same row and make the R3 elements as 0. Okay, so I have done R3 minus 2 into R1. R3 minus 2 into R1, that is R3 is equals to 4, 1 and 2 minus 2 into R1. Okay, so finally I'll get this 4 will reduce to 0 as I have multiplied 2 with R1, that is 2. So it would be 4, it's also 4. I'll get a 0 here, minus 7, 6 and here a 30. That is minus 30, sorry. Okay, so now I'll divide this by minus 3 and I'll divide R2 by minus 3, so I will diagonalize it and at the same time make it an identity matrix. So it is minus 3, here I'll divide it, and by minus 2 I'll divide the first equation. Okay, so I'll get 2, 1 in the diagonal elements. Now I am left here with a third equation in which I have to make this 7 also 0. So to make that 7 0, I have applied the row transformation R3 as R3 plus 7 into R2. I'll get a 0 here and so on. Now I have to make this 6 as 1, so I'll divide whole equation by minus 6. Whole equation is divided by minus 6, whole row is divided by minus 6, and so I'll get a 1 here. Now R2 and R3 have been diagonalized, and also we are having 1 1 in on both the diagonals. Now the thing which I have to do is to do with the row 1. I have to make this 2 as 0. So the thing which I have applied is I have subtracted row 2 from row 1 by doubling row 2. So I'll get 0 here in place of 2 when I'll subtract these two rows, and then I also need a 0 here at the place of 1. So I'll simply subtract R3 from R1, and finally I'll get this. So the values of this equation will be minus 55 by 8, 20 by 3 and 25 by 9, which are the values of x1, x2 and x3. Now finally the last question, in which we are given the population of a city in some of the years like 1921 to 1981, 35, 42, 58, 84, 120, 120 and 220. Okay, so here we need to find out the population in the year 1925. Okay, so we'll consider x as 1925 and we need to find fx. here we'll use the forward difference formula, that is this one, f1 plus forward difference of f1 by h into x minus x1 plus second forward difference of f1 upon 2h square into x minus x1 into x minus x2. For this again we have to make a forward difference table. We'll make it. Then now we know that x2 minus x1 is h, x3 minus x1 is 2h, and when we go on further we'll get xn minus x1 is equals to nh. So we'll write a generalized formula, that is x minus x1 is equals to uh. Now by equation 1, that is this equation, forward difference formula, we have fx is equals to f1 plus forward difference of f1 upon h, and this will make x minus x1 as uh, x minus x2 as u minus 1 into h. So here we are left with this equation, f1 plus forward difference of f1 into u plus second forward difference of f1 into u minus u1. So what is u here? We have to find the value of u. So we know that a plus hu is equals to x. Here a is the first value in the value of the function in the table, that is 1921, plus h is 10u plus x is equals to 1925. It is the point where we need to find the value of the function, and so here we'll get u is equals to 0.4. Now by equation 2, substituting the values of f1, forward difference of f1 and second forward difference of f1, we will get the value of the function at 1925 is 36.5. Since the population cannot be in decimal, so we'll round it off to 37. The next thing which we need to find out is population in 1975. As 1975 is near the end, so we'll use backward shift formula here. Here backward shift formula will be using f7 as the iteration, as the first value, that is as fa, and here we'll apply the backward shift operators. Okay, so again the formula is same as the forward shift, just here the difference is that x minus x7 will consider it as h, but x minus x6 is u plus 1, as x6 comes before x for 7. Yeah, so we have done u into u plus u1. Okay, now an, that is the last one, an plus hu is equals to x. Here an is equals to 1981, that is the last value, plus 10 into u plus here is equal to 1975, that is x. Okay, so here we are having u as minus 0.6. Again we'll substitute the value of u as 0.6, function value, forward difference value, second forward difference value, and we'll get 148 as the value of function at 1975. So the population of the year in 1975 is 148. The last thing which we need to find out is population in 1984, but 1984 lies outside the table, so we will assume that it will follow the same trend as inside the table. So we'll find first the value of u, that is 1984 minus 1981 upon 10, we'll get 0.3 here. Again using the same formula of backward difference that we have used here, this one, yeah, we will use in finding the population in 1984. We have substituted the values here, and finally we'll get 269.5. We'll round it off to 270. So the population in year 1984 will be 270 if it will follow the same trend. Okay, thank you so much. Have a nice day.